Welcome to the online course on risk and reliability of offshore structures. We are talking about lectures on module 1. In module 1, we are essentially focusing probability and plausible reasoning. In this lecture, which is the 10th lecture, we will introduce you some characteristics of random variables. What are random variables? How they can be simulated, how they can be modeled, or how they can be assembled for a given analysis. Before we move into the discussions of random variables, let us recollect what we discussed in the last lecture. We said that hypothesis is very important for sampling statistics in probability and plausible reasoning. Let us talk about simple and compound hypothesis. The hypothesis what we discussed so far in the last lecture are referring to generally a single parameter, where single parameter f can be simply m by n. Such hypotheses are otherwise called as simple hypothesis. Because in the space, let us say, of events sigma, of all parameters that are possible for an analysis, f is represented only by one single point. That is why it is called simple hypothesis. However, in many cases one will be interested to test the hypothesis for the parameters lying within some subset of the space value. We are not interested for the entire space of events, we are interested only in a range of space of events, while particular value of failure f one may not be interested for, or one may be very much interested. So, on the other hand, physically if a space of event is very large, you are not interested in finding out the analysis or for the entire set of range of space of events. You are interested only in certain range of this, or you may not be interested in certain range of this. So, in that cases, how will we actually handle these problems? Now, let us say one is interested in only one set of values of failure. Let us say let one is interested in only one set of values of probability of failure. Let us call this as f. Let us say, for example, f greater than 0.1, one will be interested. But of course, in the space of events 0 and 1. So, in the space of events 0 and 1, one is interested in knowing or analyzing the situation only for f exceeding 0.1. Therefore, now the revised subset for the analysis is, let us say, I call this as sigma 1, where I say now my subset is 0.1 to 1, because I am interested in values exceeding 0.1. Kindly see that one is not interested in certain actual values of f. Okay? On certain actual values of f, one may not be interested. For example, if the value is less than 0.1, it does not actually simulate to any failure. Okay? Such values are called nuisance parameters. The values of f, of course, within the subset where one is not interested are called nuisance parameters. So, if the chosen problem has no other parameter other than the variable f and their difference interval is df, which are mutually exclusive, then a discrete sum rule can be directly applied, what we discussed so far. So, if you got only f values and the interval is df which you are interested in, then one can apply the discrete sum rule. Why I am saying discrete sum rule? Because I am interested only on a specific interval of the subset sigma 1. Okay. Then I can write probability of A1 plus A2 and so on plus An given dx. We already know d is the results of the hypothesis of the tests conducted, experiments investigated. Given dx can be simply said as summation of I of probability of Ai given dx. Let me call this equation number 1. Now, the above equation, which is 1, can be also generalized into an integral form as the variable Ai becomes more numerous. In that case, one can easily get rid of the nuisance parameter by integrating it. Let us see how. So, probability of given dx, where I am looking only at the subset, is given as f sigma 1 fn 1 minus f n minus n, where capital N is the total set of values what you have observed and n is the value which has failed in that. G of f given x dx divided by f of the original subset sigma fn 1 minus f n minus n g of f given x. Let me call this as equation number 2. In case a uniform prior PDF is available to you for a single parameter f, if a prior PDF, that is probability density function of f is available, or I could say it is known to me, then the integral given in equation 2 reduces to an incomplete beta function. Let us say that is given by probability of A less than f less than b given dx. Remember, A and B represent specific events as we discussed in the last lecture, which can be now said as n plus 1 factorial by n factorial n minus n, integrating from the limits of interest A to B fn 1 minus f of n minus n for equation number 3. A set of discrete hypotheses can always be identified by one or more numerical indicates or indices which can identify them. In such cases, hypothesis testing transforms into a problem of estimation. Okay? That is the importance of hypothesis testing, where we can handle it as simple and compound hypothesis as we just now saw in few minutes. Let us now talk about a different kind of set of variables available which are actually useful in doing reliability analysis of offshore structures, what we call as random variables. Now, let us quickly see physically to understand what do you mean by random variable. Why variable we all know can take any value in a given analysis, but why the randomness? Is it assigned to the variable because the variable can take any value, or is it assigned because we do not know the value what the variable takes? Random variable is not so called as a random variable because it can assume any value. It is not called as random variable because it can assign or it can assume any value. It is not because of this reason we call this variable as a random variable. The value assigned to the random variable is not random. The value assigned to the random variable is not random, but it is fixed. Then why we call this random? Randomness is essentially due to the fact that the assigned value to this variable is not known. So, randomness is due to the fact that the assigned value, which is actually a fixed value, is not known. So, since the value is not known, you will be guessing this value in a wide range. That is why we say it is randomness. It is being guessed in a wide range of possible values. These variables are termed as random variables. Is that clear? Now, random number is therefore a representation of the event that has randomness associated with itself. It is only a convention to deal with a random event mathematically. Let us quickly see how do we generate these random numbers. There are many ways of doing it. Let us say I have a specified distribution. I want to generate random number to fit into a specified distribution. Let us say sequence of random numbers xi. Let us say let xi be a sequence of random numbers. So, xi is actually xi where I can be 0, 1, 2 and so on from a non-uniform probability distribution defined by the cumulative density function, which can be generated as below. So, I have an existing a predefined CDF. I want to generate a random number to fit to this CDF. So, what do I do? First, generate a sequence of uniform random numbers. Let us say from 0 to 1, where ui and I can take any value from 0 and so on. Then determine xi as f minus x of ui and I varies from 0, 1, 2 etc. This procedure operates by setting an area corresponding to u less than ui under uniform PDF. So, this of course sets an area corresponding to u less than ui, which is under an uniform PDF. That is very important. I am trying to fit a random number for an existing distribution. Now, in this case there is a basic assumption. It is assumed that the area will be equal to this area will be equal to the area corresponding to x less than xi or equal to xi under the PDF of interest. I can draw this graphically as you see here. Let us say I have a curve, say this is my x, this is my u, and I have an uniform curve here. So, this value of course corresponds to 1. Let us say this area corresponds to ui and this area, let us say not the complete area, but the corresponding area. How do we get this? Let us say I have a corresponding area which is only up to here. So, I have a corresponding area, I mark a corresponding area here. Okay. So, this is u1 and of course, this is my x, and this area now, this area will be equal to u1, which is an assumption that is going to be f of x xi. So, for x to follow a standard normal distribution, one should generate pairs of random variables u1 and u2 uniformly. For x to follow a standard normal distribution, one should generate a pairs of random variables. Let us say u1 and u2 uniformly. And this should be distributed in the range 0 to 1. So, how to generate this? We can use the following equations. Let us say x1 and x2 square root of 2 natural logarithm of u1 sin 2 pi u2 square root of minus 2 logarithm of u1 cos 2 pi u2, call equation number 2. If you look at this equation, please see that if the uniform random variables are statistically independent, then the standard normal random variables generated using the above equation 2 will also be statistically independent. So, let us now talk about multiple random variables. A set of random variable y which will be y1, y2, y3 till yn which is actually a joint random variable, which means that m, the vector m and the covariance matrix sigma. One need to generate the sequence of random numbers or random variables that are statistically independent. One can use the following relationship for this. Let us say x can be x1, x2, xn transpose, and now if you want to generate y, simply say it is Lx plus m, where m is the mean vector and sigma is the covariance matrix. Call the equation number 4. In this case, L is the lower triangular matrix This can be found out from Cholesky decomposition, which can be determined using Cholesky decomposition. Of the covariance matrix. That is, one has to fulfill the requirement that L transpose should be the covariance matrix. I call this equation number 4a just in continuation with the set of equations written there. Now, you have to repeat this procedure n number of times for how many variables you want to generate as multiple random variables. There is another way by which you can generate random variable, that is what we call nut of random variables. Now, to generate nut of type random variable of y equals y1, y2, yn transpose, which is now a vector of nut of distributed random variable with marginal cumulative distribution functions, with marginal CDFs, and the correlation coefficient matrix R is of size. The correlation coefficient matrix R will have a size n by n, because n is the number of variables you are generating. One can generate now a sequence of n random variables which are statistically independent. One can use the following relation. Let us say Z is L naught x, where L naught is the lower triangular matrix, that satisfies L0, L0 transpose is my R0, where R is the correlation coefficient matrix. Now, R0 of course is the modified correlation coefficient matrix for the nut of random variables. Now, the outcome of this generation will be determined as follows. We know y is y1, y2, yn transpose. So, I want to establish and expand this, say y1, y2, y3, yn is now equal to f y1 inverse phi of z1 Similarly, f y2 inverse phi of z2 and go on f yn inverse phi of z. I call this equation number 6. One can repeat this above procedure n number of times as many y or variables you require. So far in the previous cases we saw that I have a predefined prior understood distribution whose PDF and CDF are known to me. I am trying to fit the random variable for an existing prior defined distribution. Now, I want to now generate random variable by conditional distribution. Let us say I want my random variable should obey a type of distribution. So, random variable generated by conditional distribution to generate an outcome of a vector which is a random variable whose joint PDF, let f of x is the joint PDF defined by the conditional distribution. One is interested to generate a sequence of n statistically independent uniformly distributed random variable which is given by this. So, they should be statistically independent and uniform distributed random variables. Then one can apply Rosenblatt transformation as I am now writing here. So, applying Rosenblatt transformations one can get x1 is fxi inverse of u1, x2 fx2 x1 inverse of u2 given x1 and so on. So, in such case I can write a general expression xn fxn xn minus 1 xn minus 2 of inverse x1 of u1 given xn minus 1 xn minus 2 till x1. Call equation number 7. The above set of equations what will generate will have conditional CDFs of xi. The conditional CDFs of the above equations will be, let us say x1 will be x1, xi minus 1 will be xi minus 1, similarly xi minus 2 will be xi minus 2. One can repeat the above procedure as many outcomes as you want for x, which will be a random set of variable which will be statically independent and they will obey to a conditional distribution. Alternatively, one can also use Monte Carlo simulation. In this simulation of random variables, the main problem actually lies with the evaluation of specific function, which is this function. So, the difficulty is with evaluating the following function. Integral for x I of x f of x dx, where I of x is an indicator function which is given by okay, 1 and 0 if is an element of sigma or otherwise. Equation 9, where sigma is qm intersection I element of Cm of the function Gix less than 0. Now, let us say Qi is I xi, where xi is the ith random sampling of x. Then P of Qi equals 1 will be the probability of failure, and P of Qi equals 0 will be 1 minus probability of failure, which is reliability. So, Qi I can be from 1, 2, 3 etc., which are statistically independent. Of course, Q1, Q2 are Bernoulli sequence. Which can be given by the following equation. Qi can be given by 1 of Pf plus 0 of 1 minus Pf, which actually Pf, and variance of Qi can be said as expected value of Qi square minus expected square value of Qi. We all know for Bernoulli's variable, for let me call this equation number 11, for Bernoulli variable Qi square is same as Qi. Therefore, the equation can be rewritten as variance Qi can be simply or one of Pf plus 0 of 1 minus Pf, I am substituting back, minus Pf square. That is what I will get as Qi. Alternatively, one can also express probability of failure as expected value of indicator function. So, one can also express probability failure as expected value of indicator function, that is probability of failure is expected value of I of x. Estimate of probability of failure is then given by probability hat failure is expected value of the indicator function, which is nothing but 1 by n of summation of I equals 1 to n q y, which is q bar, where q bar is the sample mean obtained from n simulation of random vector x. It is important, dear friends, to see that the probability of failure is also a random variable in the present simulation. Therefore, the expected value of this estimator is given by, so expected value of p hat, I am talking about p hat, I will then connect it to probability of failure, which can be given by the expected value of 1 by n of summation of q y I 1 to n, which can be also said as 1 by n probability of failure which can be simply probability of failure. Oh, this is equation number 13. Now, we will get probability of failure hat as an unbiased value, hence p hat failure will be an unbiased estimator of probability of failure, and the variance of p hat failure can be given by variance of p hat failure is variance of 1 by n of summation of I equals 1 to n of q I, which can be 1 by n 2 of variance of summation of I equals 1 to n of q y, which is nothing but 1 by n 2 of variance of q y, which can be said as 1 by n of probability of failure 1 minus probability of failure. Equation number 14. Now, the coefficient of variation and further discussion of random variables using Monte Carlo simulation will be discussed in the next lecture. So, in this lecture we have discussed about some specific characteristics of random variable, how one can generate a random variable using a conditional distribution, how one can fit the generated random variable for a predefined a prior known PDF and CDF for a given function. I hope you will follow this lecture. Try to look into the support material from references given in the NPTEL website. Should you have any difficulties or questions, please post to me. We will try to explain as clear as possible. Thank you very much.